The universe speaks. It communicates through numbers. These numbers are known as constants. They form the very bedrock of our reality, the unwavering foundation of all that is, unchanging, steadfast, absolute, or at least that is what we have long believed. These values meticulously define our existence. They are the architects of the cosmos. These are not merely random sequences of digits. They represent profound cosmic laws, elegantly encoded within the language of mathematics. They are the keys to unlocking understanding, from the breathtaking vastness of interstellar space to the infinitesimally small realm of subatomic particles. The entire edifice of science rests upon them. They are our most trusted guides through complexity, illuminating the hidden workings of nature. But what happens if such a guide appears to point in two opposing directions? What if a fundamental constant conceals a truth long overlooked, a subtle reflection previously unseen by searching eyes? For many decades, the world of physics has placed its faith, perhaps at times a faith too unquestioning. Now is the moment to peer more closely, to re-examine the very pillars of our knowledge. Two specific numbers stand exceptionally tall. They are the undisputed pillars of modern scientific thought. The first is c, the immutable speed of light. The second is h, the enigmatic Planck's constant. One represents a cosmic speed limit, an ultimate velocity, the other a fundamental quantum measure of action. Their individual stories are deeply, inextricably intertwined, perhaps far more profoundly than we ever dared to imagine, a connection that holds surprising revelations. Albert Einstein, his name itself is a synonym for transformative genius. He perceived light in a revolutionary new way, not simply as a source of illumination for our world, but as a fundamental structuring rhythm of existence, the very pulse, the heartbeat of the entire cosmos. CORE, the speed of light, was his unwavering cornerstone. He saw it as integral to the structure of reality itself, a constant that shapes space and time. His iconic equation reverberates through the halls of science. E equals mc squared, energy, mass, and the speed of light. Three concepts forever and indivisibly linked by his insight. The term Ci squared reveals itself as a mighty multiplier. It demonstrated light's almost incomprehensible, immense power. He portrayed light as a dynamic, universe-shaping force, the ultimate, unsurpassable speed ordained by the universe, a boundary that nothing with mass could ever break. Then there was Max Planck. He courageously peered deep into the nascent quantum world, a strange, almost alien realm composed of tiny, discrete packets. He posited that energy was not a continuous, smooth flow. Instead, it arrived in distinct, quantifiable steps or jumps. He meticulously calculated and gave us a number for this. That number is h, known universally as Planck's constant, a precise defining measure of this fundamental quantum leap, the smallest unit of action possible in nature. Two titans of thought, two distinct yet related perspectives. Einstein was captivated by light's majestic, continuous flow, its uninterrupted wave-like journey across the cosmos. Planck, in contrast, focused on quantifying its energy packets. He painstakingly calculated its defining constant value, but within that very calculation, a critical choice was made, a specific direction was chosen, a path was taken, and perhaps another path was unknowingly left unexplored. This divergence would have profound consequences. Physics carefully constructed its magnificent house. It was built upon these seemingly solid, reliable foundations. The speed of light, c, and Planck's constant, h. Both were widely believed to be absolute and unassailable. But what if one of these crucial foundations was not precisely as it appeared to be on the surface? What if it harbored a subtle yet powerful distortion? A hidden secret camouflaged within its numerical precision, a secret that could alter our understanding. Einstein masterfully unveiled the grand tapestry of the universe. His groundbreaking formulas painted the vast cosmic big picture, interweaving light, energy, matter, and the fabric of space-time. Planck, with equal brilliance, provided the essential fine detail, the incredibly precise numerical value of h. This value defined the almost infinitesimal scale of the quantum, yet this celebrated precision held an unexpected, curious twist. A hidden duality lay dormant within its digits. waiting patiently for discovery or perhaps for admission, within the very structure of Planck's number. The sequence of digits that constitute the constant h lies an unforeseen, almost unsettling pattern, a mirror. It appears to reflect the speed of light, c, not in a direct, straightforward manner, but in reverse, a kind of shadow image, an inverted echo. For generations, science, in its forward momentum, never looked deep enough. It never truly gazed into this peculiar looking glass. The implications of this reflection remain largely unconsidered. Two remarkable men indelibly shaped our modern physics. One profoundly understood the essential rhythm and structure of light. The other meticulously measured its fundamental quantum nature. But the resulting measure, the constant itself, contained a mirror, and the keeper of light's rhythm, Einstein, remained silent. Why? This question hangs heavy in the air. It is a silence that echoes through the decades. As St. poignantly stated, whoever makes light the standard must not calculate it through its reverse. A truly haunting and provocative thought to consider. At the dawn of the 20th century, a new number emerged. It was a figure of profound, almost infinitesimal smallness. This number is known as Planck's constant, symbolized by h. Its accepted value is meticulously precise, 6.62607015 times 10 to the power of minus 34 joule seconds. This constant arose from Max Planck's groundbreaking work. He sought to understand the puzzling nature of black body radiation. Little did the world know this number held more than just a value. It held a key, a definition for energy and time at their most fundamental, a cornerstone of the strange and wonderful quantum realm. Planck's constant dictates the very graininess of our universe. It tells us that energy is not continuous but comes in discrete packets. These packets are called quanta, the smallest possible units of energy. Imagine a staircase, not a smooth flowing ramp. Each step represents a quantum jump defined by h. This concept revolutionized physics, birthing quantum mechanics. It underpins our understanding of atoms, of light, of reality itself. The constant acts as a fundamental scaling factor. It defines the boundary between the classical world and the quantum. This number, h, is more than a mere descriptor of energy packets. It intrinsically links energy to frequency and, by extension, to time. The energy of a quantum of light, a photon, is directly proportional to its frequency, and h is the constant of that proportionality. It speaks to a deep relationship between what something, energy, and how it over time, frequency. This humble constant became a pillar of modern science, a testament to Planck's relentless pursuit of understanding. Its influence stretches across vast domains of physical inquiry. Yet within this celebrated figure, a deeper layer has remained, largely unexamined, hidden in plain sight for over a century. Beyond its role as a fundamental unit of action, beyond its quantification of quantum phenomena, there lies a numerical pattern, a subtle characteristic. A characteristic that connects it surprisingly and unsettlingly to light itself. This constant, so crucial for understanding the small, might also reflect the grand, the cosmic speed limit c, but in a way that was perhaps never intended or fully grasped. Let us now look closer at the digits of Planck's constant. The sequence, 6.62607015, and compare them with the digits of the speed of light, c's. The cosmic speed limit, 299,792,458 meters per second. At first glance, they appear as distinct entities serving different roles. One defines the quantum scale, the other a universal velocity. But a curious correspondence emerges upon careful inspection, a pattern not of direct repetition but of reflection, as if one number is gazing at the other through a distorted lens. Consider the initial digits of Planck's constant, 6.62. These numbers bear a resemblance, a numeric echo to parts of 299, the leading figures of the speed of light, 299, 792, 458. It is as if the commencement of h acknowledges c, but it does so in a veiled, almost shy manner. This is not a game of chance, not mere numerology. It is presented as an observation of numeric symmetry, a structural kinship hidden within the fundamental constants that govern our physical reality, demanding our attention. The pattern continues, becoming even more intriguing. Look at the latter part of Planck's constant digits, 607015. The brief suggests that if one considers an inversion of this sequence, or a specific transformation, it yields something akin to 992. These digits, 992, strikingly mirror the initial part of CQ 299, or more precisely, 299 from 299, 792, 458. The relationship is not straightforward, it is mirrored, reversed. Planck's constant seems to contain an imprint of the speed of light, but it is an imprint that has been turned back upon itself. This numeric symmetry is a subtle yet profound observation. It suggests that Planck, in formulating his constant, did indeed incorporate the essence of light. How could he not? His work was on radiation, on light itself. But the method of incorporation was not direct. It was not an embrace of light's inherent directionality. Instead, it was a reflection, a mirroring. The constant captures aspects of C, but presents them inverted, as if light's properties were viewed through a looking glass. This act of mirroring light, rather than following its natural flow, had significant conceptual consequences for physics. When a value is inverted, its intrinsic meaning can shift. Its relationship to other phenomena can be subtly altered. Planck's constant, by reflecting CE in reverse, set a different course for understanding energy and light. It was a choice embedded deep within the mathematics, a choice that would ripple outwards, shaping theories and influencing the interpretation of countless experiments. The result of this mirrored approach was profound. It led to what can be described as a frequency cut. Instead of embracing light as a continuous resonance, a wave propagating with an inherent rhythm and structure, the focus shifted towards discrete packets, static quantities. Planck's constant became the measure of this segmentation, defining the smallest possible slice of action, of energy. This was undeniably powerful for quantum calculations. But did it obscure a more holistic view of light's nature? Imagine light as a flowing river, a dynamic wave, its energy and momentum carried by its continuous current. The mirroring within Planck's constant, however, encouraged a view of this river as a series of distinct droplets, each droplet a quantum, defined and limited by egg. This perspective transformed light from a dynamic wave into a collection of particles, or static quantifiable units. The wave nature was still acknowledged, of course, but the emphasis tilted, subtly yet decisively, towards the particle, towards the static quantity rather than the unfolding dynamic. This was not an error in calculation, not a mathematical mistake. Planck's constant remains an incredibly accurate and useful tool. The divergence was conceptual, a shift in fundamental perspective. By embedding a mirrored image of light's speed into h, Planck unwittingly oriented physics towards a particular interpretation, an interpretation where constants define static limits rather than describing dynamic relationships and open resonances. This choice, perhaps unconscious yet numerically evident, cast a long shadow on the trajectory of 20th century physics, setting the stage for a science of jumps, not of flows. Albert Einstein knew Max Planck well. Their paths crossed, their ideas intersected. Physics was a smaller, more intimate world then. Planck was an established figure, a pillar of the old guard. Einstein, the young revolutionary, challenging classical thought. Yet a deep respect existed between these two colossal minds. Planck was among the very first to recognize Einstein's genius. He championed Einstein's groundbreaking 1905 papers. This early support was crucial for the then unknown patent clerk. Einstein did not merely acknowledge Planck's work, he actively incorporated Planck's constant into his own theories. The most famous instance is his explanation of the photoelectric effect, a puzzle that classical physics simply could not solve. Light, Einstein proposed, behaved as particles, photons. The energy of each photon was directly proportional to its frequency. The constant of proportionality, Planck's AH, E equals h times F, A simple equation, yet profoundly transformative. It was for this work, not relativity, that Einstein won the Nobel Prize. This adoption of H was a powerful endorsement. It demonstrated the utility, the necessity of Planck's quantum. Einstein used H to unlock secrets of light and matter. He wielded it as a key, opening doors to new understanding. The constant became an indispensable tool in his toolkit. It allowed him to quantify the very essence of light's energy. This was not a casual use, it was fundamental to his reasoning. The constant validated the idea of quantized energy, a concept that was still radical, still being debated fiercely. So Einstein, the master of light's rhythm, used H. He built upon the foundation Planck had laid. His work with the photoelectric effect cemented H in physics. It became a cornerstone of the burgeoning quantum theory. There was no outward sign of rejection, no public questioning, at least not of the constant's fundamental utility. The number worked, it produced results, it explained phenomena, but utility does not always equate to complete conceptual alignment, especially when considering the subtle mirror within. Section 2. A knowing silence, the rhythm disturbed. Einstein felt the universe's harmonies deeply. For him, seeing the speed of light was a fundamental rhythm of space-time. Light's constant speed defined reality's fabric. This understanding was core to his thought. He perceived its wave-like nature, its continuous flow, a cosmic dance of energy and momentum. When he encountered Planck's constant H, did he sense the subtle inversion of C? The essay suggests this numerical symmetry is not mere coincidence. Yet the historical record shows a conspicuous silence. Einstein engaged in debates about quantum mechanics. But the intrinsic structure of H itself, its mirrored digits, does not appear as a prominent subject of his critiques. Why did he not publicly address the constant that seemingly inverted its echo? This silence resonates with unanswered questions. Was it an oversight or a deliberate omission? A quiet puzzle at the heart of quantum beginnings. Section 3. Whispers of why, the unspoken compromise. Why would Einstein remain silent? Several factors might have contributed. Perhaps a profound sense of gratitude played a role. Max Planck was a towering figure in German physics. His support for Einstein's relativity was invaluable. To critique Planck's constant might have felt like a betrayal. Then there were the dynamics of scientific politics. The early 20th century was a period of immense upheaval. Planck's constant was becoming a cornerstone of quantum theory. To question it could be perilous. It might have been perceived as an attack on the burgeoning quantum field, a field that Einstein helped to initiate. Challenging such a fundamental constant could isolate him. Furthermore, there is the possibility of fear of disrupting a system that worked. Planck's constant yielded results, advanced science. To introduce a critique based on numeric symmetry might have seemed less urgent. Perhaps he feared destabilizing progress. Ultimately, Einstein allowed the structural rhythm of light to be represented by a constant that contained a mirrored inversion. This decision had lasting consequences. Section 1. Unveiling the frequencies, Planck's H as a wave. Planck's constant H defines the quantum of action. Its value is etched into modern physics, but what if H harbors a more dynamic identity? Consider H as representing a fundamental frequency. This is not to dispute its established role, rather it is an attempt to unearth a hidden dimension. If H embodies a characteristic frequency, what are its defining features? The implied wavelength suggests a vibration on a plane far removed from our everyday experiences. This hints at a primordial vastness. Section 2. The dance of digits, symmetry and wavelengths. If we interpret H as representing a wavelength, it extends across magnitudes far exceeding any known natural scale. This immensity serves as a profound clue. Consider the speed of light, c, precisely valued. The source material highlights a perfect 1-meter symmetry associated with CEE. This suggests a fundamental correspondence between c and the meter. The meter is defined by the distance light travels in a vacuum. This symmetry implies a natural coherence between light's propagation and our measure of space. Juxtaposing H and CE, we observe a profound dialogue. H speaks of the quantum realm's defining unit. CE speaks of the universe's ultimate speed limit. Section 3, Entangled Echoes, the inversion's impact. The re-emergence of C from the interplay of H and C signifies their interdependence. Planck's constant H is not isolated, it is tethered to C. This entanglement is a profound structural bond. The defining characteristic is the inversion, the mirror. Planck's constant reflects C in reverse. This inversion is the critical point. It creates a relationship forged in opposition. This inversion translates into a tangible, broken interpretation of physical reality. The balance of wave-particle duality might be tilted. Einstein's silence allowed this inverted perspective to take root. Physics built upon a constant with a reversed echo of light. This contributed to a conceptual misstep in understanding the quantum world. Section 1. Light's new guise, the particle ascendant. The mirror embedded within Planck's constant did not merely reflect light's numerical signature, it fundamentally reshaped our perception of light itself. Before this subtle inversion took hold, the understanding of light was increasingly leaning towards its nature as a continuous wave, an electromagnetic structure weaving through the cosmos. Einstein, more than anyone, championed this view, seeing C not just as a speed, but as a defining characteristic of space-time's very fabric, a fundamental structural rhythm. Light was the universe's grand narrative, unfolding seamlessly. This perspective emphasized its connectedness, its flow, its inherent ability to bridge vast cosmic distances as an unbroken entity, a messenger of cosmic design. Yet the advent of Planck's constant H, with its intrinsic focus on quantization and its hidden numerical mirror, began to steer this understanding down a different path. The concept of the quantum, the discrete packet of energy, became inextricably linked to light through H. This gave prominence to light's particle aspect, the photon. While wave-particle duality is an accepted cornerstone of physics, the mirrored constant subtly favored the particle interpretation in foundational thought. It encouraged a view where light, especially in its interaction with matter, was primarily a volley of tiny bullets rather than an embracing wave. The mirror, by presenting a reversed echo, fragmented the holistic view of light's continuous structural essence. This shift towards light as primarily a collection of discrete particles, influenced by the static slice interpretation that the mirrored H implies, had far-reaching consequences. It subtly moved our conceptual framework away from seeing light as an active structuring agent of the universe, a dynamic weaver of reality's tapestry. Instead, light increasingly became a passive messenger, a stream of information carriers operating a pre-existing, somewhat static arena of space and time. The mirror, by inverting the directional essence of light's structure, inadvertently demoted its role from architect to courier. This changed how we formulated questions about light's ultimate nature and its role in cosmic evolution, focusing more on its particulate interactions than its overarching structural implications. Therefore, this was no mere academic adjustment in terminology or a minor refinement of theory. It represented a profound conceptual divergence, a fork in the path of understanding. By choosing the path illuminated by H, the path of discrete, quantifiable packets influenced by this subtle yet potent numerical inversion, physics embraced a specific facet of light's multifaceted nature. This emphasis, however, may have inadvertently led us to overlook, or at least de-emphasize, the deeper, more holistic implications of light as a continuous, fundamental structuring principle of existence. The mirror within the constant cast a long shadow, subtly altering the image of light for generations of scientists. The conceptual transformation of light from a flowing structure to a series of discrete particles inevitably cast its influence upon our understanding of time. If light's very essence, its continuous rhythmic propagation, defines the pulse of the cosmos, then a constant that segments light into static mirrored packets would surely alter how we perceive time's passage. In classical physics, and particularly within Einstein's relativistic framework, time was intimately, dynamically interwoven with the speed and nature of light. It was not a passive backdrop, but an active dimension. Its flow intrinsically linked to the universe's structural rhythms dictated by CE. This was a time with inherent dynamism, a flowing river alongside which the universe unfolded. However, the quantum revolution, with Planck's constant h at its very core, began to subtly reframe the conceptualization of time. In many quantum mechanical formulations, time often assumes the role of an external parameter, a coordinate, a kind of universal clock ticking independently in the background. It becomes the axis against which quantum events, such as the emission or absorption of energy packets, are plotted and measured. The emphasis on discrete energy states, defined by h and frequency, E equals sign hf, indirectly encourages a view of time as a sequence of moments where these quantum jumps occur, rather than as a continuous, flowing entity whose rhythm might underlie these jumps. The mirror in H segmented energy, and by extension it subtly segmented our view of time's role in these processes. This shift carries profound consequences. Time, in certain influential quantum interpretations, risks losing some of its inherent dynamism, its active participation in the cosmic dance. Instead of being a fundamental rhythm, a beat intrinsically connected to light's structural unfolding and the universe's expansion, it can be perceived as a more abstract, somewhat passive dimension. A ruler for measuring intervals, a number in our equations. The mirrored nature of Planck's constant, by championing static slices of energy and action, inadvertently contributes to this conceptual flattening of time. It promotes a view where events happen time rather than time itself, being an unfolding process intrinsically shaped by the universe's energetic and structural dynamics. Reflecting on this transformation, from time as a cosmic beat to time as a measured tick, we must consider its potential limitations. Such a shift might constrain our ability to fully comprehend phenomena that truly depend on a deep, continuous temporal flow, processes that transcend simple discrete steps. If the universe operates on underlying rhythms that are more fundamental than our quantized measurements suggest, a perception of time heavily influenced by the static slices of a mirrored H might obscure these deeper realities. The mirror, by focusing on the quantum event, may have inadvertently encouraged us to look at the ticks of the clock, perhaps missing the profound mechanics of the clockwork itself. The profound conceptual shifts in our understanding of light and time stemming from the mirrored nature of Planck's constant naturally extended their reach to the very concept of energy. Energy, inextricably linked to Planck's constant through the foundational equation E equals sign hf, could not remain untouched by this subtle yet pervasive inversion. In the classical view preceding the quantum revolution, energy was often conceptualized as a continuous fluid, a quantity capable of smooth, gradual changes and modulations. It could ebb and flow, increase or decrease with seamless grace, much like the gentle rise and fall of a wave. This perspective allowed for a universe where energetic processes were, at their core, smooth and connected. Max Planck's revolutionary proposal, encapsulated by the constant R, introduced the radical idea of energy quantization. This meant energy could only be absorbed or emitted in discrete, indivisible packets, the quanta. This was not a mere theoretical construct. It was a concept born from experimental necessity, explaining phenomena like black body radiation. However, of these energy steps, significantly influenced by the inherent mirror within H, is what commands our attention here. The mirror, by its nature of reflecting and segmenting, reinforced the step-like character of energy transactions. It subtly steered the interpretation towards these steps as being the fundamental reality, potentially overshadowing the possibility of an underlying continuous energetic modulation from which these steps emerge. This emphasis on energy as a series of discrete steps rather than a continuous flow solidified the quantum jump paradigm as a central tenet of understanding the subatomic world. Systems were seen to transition abruptly, almost instantaneously, from one allowed energy state to another without traversing the intervening energetic landscape. This model has been extraordinarily successful in predicting and describing quantum phenomena. Yet the question lingers: Are these jumps the ultimate irreducible reality, or are they perhaps the observable manifestations of deeper, more continuous modulations occurring within an underlying energetic field, a field whose continuous nature might be conceptually obscured by a constant that emphasizes division and reflection, the static slice over the dynamic wave? In conclusion, these interconnected transformations, light becoming predominantly particle-like, time shifting from a cosmic rhythm to a numerical parameter, and energy being perceived as discrete steps instead of a continuous modulation, represent more than just subtle refinements in scientific description. They signify a major conceptual detour in the journey of physics. This detour, arguably guided by the subtle yet powerful influence of the mirrored inversion within Planck's constant, profoundly shaped the landscape of 20th century physics. We effectively traded the logic of standing waves and continuous structures for the paradigm of quantum jumps and static slices. The directionality inherent in light structure was replaced by the fixed, reflected quantities defined by h, setting physics on a course whose full implications we are still endeavoring to comprehend. Our journey into the heart of Planck's constant h now takes a deeper turn. We have explored its numerical structure, its unsettling mirror of light speed, Ci, and the profound silence of Einstein regarding this inversion. The consequences, we have argued, led to a physics where light became a particle, time a mere tick, and energy a series of jumps. But what if, even within this mirrored framework, the true resonant nature of light still attempts to make itself known? What if there are hidden patterns, subtle harmonies that persist, waiting for a perceptive ear, a gaze willing to look beyond the surface of established interpretations and assumptions? These are the questions that now guide our inquiry. To probe these hidden resonances, we consider specific vibrational signatures. Let us first examine a frequency, FE1, designated as 1.1111 times 10 to the power of 7 Hz. This value, with its distinctive repeating digits, is not arbitrarily chosen. It emerges from a deeper structural analysis related to the informational content of constants, a concept explored in TOULOUMIDIS' foundational work. It represents a specific resonant mode, a vibrational pattern that we propose is intrinsically linked to the underlying fabric of physical reality. This frequency stands apart, a unique pulse that, when considered alongside light's own signature, begins to unveil a more complex, more interconnected sonic landscape than conventional physics typically acknowledges, a landscape rich with potential meaning. Our second primary frequency, F2, is far more familiar, yet no less profound in its implications for this analysis. We take this as 2.99792 times 10 to the power of 8 Hz. This numerical value, of course, directly corresponds to the speed of light, c, expressed in meters per second, but here considered as a frequency. Light is the universe's ultimate messenger, its speed a defining limit, and its nature inherently tied to oscillation and wave phenomena. By conceptualizing Ct as a frequency in this context, we are not diminishing its role as a speed. Rather, we are seeking to understand its vibrational dialogue with other fundamental frequencies that may permeate the cosmos, creating a richer tapestry of interaction. With these two distinct frequencies, F1 and F2, now clearly defined, we stand at the threshold of a new revelation. One frequency is derived from a deeper analysis of constant structures, hinting at underlying order. The other is the very numerical heartbeat of light itself, the universe's primary rhythm. What happens when these two frequencies are brought into conceptual collision? What patterns emerge from their interaction, from their numeric interplay? The investigation into their combined properties, their sums, and their resultant wavelengths promises to uncover evidence of a persistent structural harmony, even within a system subtly distorted by the mirrored nature of Planck's constant h. Section 2, the harmonic convergence frequencies in dialogue. When these two carefully selected frequencies, F1, 1.1111, 1 times 10 to the 7th Hertz, and F2, 2.99792 times 10 to the 8th Hertz, are allowed to interact, to conceptually collide, their combined signature reveals something truly noteworthy. Their frequencies sum to a new composite frequency, approximately 3.10904 times 10 to the 8th hertz. This resulting value is not just an arbitrary number, it represents a new vibrational state, a harmonic born from the union of the elemental pulse, F1, and light's own characteristic frequency, F2. This summation is the first clue that these frequencies are not isolated entities but participants in a larger resonant system, capable of generating new, meaningful patterns through their interaction, patterns that speak a language of coherence. As we translate these frequencies into their corresponding wavelengths, using the speed of light as the conversion factor, we uncover further elegance. The wavelengths derived from F1 and F2 individually, and from their sum, exhibit relationships that can be described as forming elegant, often repeating fractions or simple ratios. The recurring digit in F1, 1.11111, itself hints at a fundamental simplicity, a purity of form that often underpins natural resonances. These are not chaotic random measures, but rather lengths that suggest an underlying order, a mathematical neatness that is often the hallmark of structurally sound systems. This elegance in their wavelength relationships further strengthens the proposition that these are not coincidental alignments, but evidence of deeper design principles at play. The analysis of these interacting wavelengths culminates in a particularly striking observation, the emergence of an average wavelength of approximately 1.92 meters. This specific length is profoundly significant because it, once again, mirrors structural patterns related to the speed of light, c, and its inherent 1-meter symmetry. A value so close to 2 meters in a system deeply entangled with c's 1-meter coherence is too precise to be dismissed as mere chance. It suggests a doubling, a harmonic overtone, or a fundamental scaling factor that echoes the primary structural unit of light's propagation. This approximately 1.92-meter wavelength acts as another layer of evidence, pointing to a persistent structural integrity. These findings are compelling. They demonstrate that even when our primary tool for quantum understanding, Planck's constant h, carries an intrinsic mirror effect, the fundamental rhythms of light and structure strive to reassert themselves. The original harmonies, the inherent mathematical elegance of the universe, attempt to shine through the distortion. It is as if the universe possesses a deep-seated preference for certain resonant patterns, for specific structural symmetries. These patterns, like the 1.92-meter wavelength, are the echoes of an underlying order, an order that the mirrored constant may obscure but cannot entirely obliterate from the tapestry of reality. Section 3. The shadow of reflection, light's obscured design. The persistent emergence of these harmonic patterns, even in a conceptually mirrored system, strongly suggests that we are often observing the universe through a subtly distorting lens. Because we rely on Planck's constant h, with its inherent numerical inversion of light's signature, we may be systematically misinterpreting or failing to fully perceive these deeper resonances. The mirror within h does not entirely block the view of this underlying order, but it certainly complicates it, making the patterns appear more convoluted, less direct than they might otherwise be. We are, in essence, trying to understand a perfectly tuned instrument while listening through an imperfect echoing chamber, which makes the true melody harder to discern. This brings us to a critical and somber reflection, articulated with stark clarity in TOULOUMIDis' quote. When light is mirrored, it doesn't just lose direction, it loses the reason why it exists at all. This statement cuts to the core of the issue. If light is fundamentally a structural agent, a dynamic principle of cosmic organization, then to perceive it primarily through a constant that inverts its directional echo is to misunderstand its very purpose. Light, in this mirrored view, becomes a collection of effects rather than a primary cause, a series of phenomena rather than the foundational process of ordering and connection that it truly represents in an unreflected framework. The implications for the entirety of physics are vast and far-reaching. If these fundamental resonance patterns, such as the approximately 1.92-meter structural wavelength, are consistently overlooked or misinterpreted due to the ingrained use of an inverted conceptual tool, what crucial aspects of light, energy, and cosmic structure are we failing to grasp? We might be constructing elaborate theories upon a foundation that, while operationally successful in many domains, subtly misdirects our search for ultimate understanding. The pursuit of a truly unified theory, one that seamlessly connects the quantum and the cosmic, might be perpetually hampered by this initial, foundational distortion in our understanding of light's fundamental nature. Therefore, the mirror within Planck's constant is far more than a mere numerical curiosity or an academic footnote in the history of science. It represents a fundamental conceptual impediment, a silent divergence that has shaped our view of the universe for over a century. By not recognizing this inversion, by not accounting for its distorting influence, physics may have inadvertently veiled the true, resonant design of light. The path forward requires not just new calculations or experiments, but a courageous willingness to re-examine our most basic assumptions about the constants that define our reality and to finally look directly at the light, unmirrored and unobscured. Section 1. The shadow of the mirror, a legacy of distortion. What began as a subtle flaw, a tiny mirror within a single number, has cast a long, pervasive shadow over science. This shadow falls across an entire century of physics. Planck's constant, the famous A, carried this hidden aspect. It became a silent, almost invisible trap. A trap for our deepest understanding of the cosmos, a trap for our very perception of fundamental reality. Modern physics, unknowingly, built its grand house within this shadow. Now, with courage, we must dare to ask the vital questions. Is Planck's constant truly an ultimate, fundamental limit, or is it, in some significant part, a conceptual distortion? A subtle reflection that inadvertently took us down a divergent path. Was light, the universe's primary messenger, ever meant to be so starkly divided? Into discrete, separate packets, into quanta, into abrupt jumps? Or was its truest essence always one of modulation, a continuous, flowing, structural wave-shaping existence? The mirror favored one incomplete view, thereby obscuring the other. This almost imperceptible inversion had profound and lasting consequences. It systematically steered physics toward particles, not holistic structures. It guided our focus toward static slices, not dynamic, unfolding rhythms. We learned to celebrate constants as absolute, unyielding boundaries, instead of exploring them as potential keys to universal resonance. The primary focus shifted towards division, towards meticulous quantification. The parallel search for a more holistic understanding was subtly sidelined. Crucial directionality was lost, confused in the mirrored reflection. A vital dimension of the universe's reality remained veiled from our sight. The legacy of this is a science of truly immense achievement, yet it is also a science that may carry a fundamental flaw at its core. A physics that describes the what of the universe with breathtaking brilliance, but perhaps it still struggles deeply with the more profound why. Why does the universe exhibit such a preference for certain structures? Why does the principle of resonance echo so consistently through the cosmos? The mirror, inherent in H, directed our scientific gaze away from these tunes. It taught us to meticulously count the beats, but not always feel the music. This is the challenging inheritance of the silent, reflective trap. Section 2, Beyond the Reflection, a New Dawn for Physics. The answer to this profound and challenging dilemma is not necessarily complex. It does not automatically lie in crafting even more elaborate equations, nor is it found solely in building more powerful particle colliders. The solution, perhaps, begins with a simpler yet far braver first step. It demands of us a thorough re-examination of our most basic foundations. The essential truth we propose resides within the structure itself, the very cosmic structure that we may have inadvertently overlooked, the inherent architecture of constants, of light, and of space. There, the original, unblemished blueprint of reality can still be found. This rediscovered path, should we choose to take it, leads us towards resonance. The universe, it seems, speaks primarily in harmonies, in fundamental vibrations. These are not merely poetic, abstract, or philosophical notions. They represent fundamental core principles of cosmic organization and being. Light, when perceived in its unmirrored, untainted glory, is a standing wave. It is a structural form, a pattern in space-time, not just a fleeting particle. Its continuous modulation carries information, generates complexity, creates order. We must therefore learn anew how to listen to these cosmic songs, to meticulously tune our theories to their inherent guiding frequencies. And what then of Albert Einstein's profound, his truly enduring silence? That notable silence, we believe, holds a crucial, still echoing message. A subtle message that we as a scientific community are only now beginning to decipher. He intuitively knew light's rhythm, its undeniable structural imperative. Did he perceive the mirror within Planck's constant and choose not to speak? Or was the full implication too vast, too unsettling for that particular era? His thoughtful silence now powerfully challenges us to break our own silence, to courageously confront the deep questions he may have left unanswered, to perhaps complete the conceptual revolution he started, then seemingly paused. The promising future of physics now beckons us compellingly forward, not necessarily along the same well-trodden, potentially mirrored path, but towards a fresh horizon of deeper, more integrated understanding, a future where light finally reclaims its true directional, structural essence, where fundamental structure and cosmic resonance confidently guide our inquiries. The immense task before us is to look steadfastly beyond the distorting reflection, to consciously decide to step out of the confines of the silent trap, and to wholeheartedly embrace a physics of innate wholeness, of continuous flow, a physics truly worthy of the magnificent light that defines and illuminates it.